Hi, welcome to the next lecture in the NPTEL series on Haskell. This will probably be the last lecture. What we will do in this lecture is that we will try to apply some of the basic concepts we have learned to write a program to solve Sudoku. Okay, so I just wanted to end on a fun note, but which also tells you a lot about the power of Haskell, etc. And this is a large programming task. Okay, so that is the good thing. So take a new problem, try to actually build a solution from scratch. This is just an exercise in building a large program. Yeah, so let's hope we have fun. Okay, let's get into it. Okay, what is Sudoku? Sudoku is just this puzzle where I have this 9 by 9 grid, and every row should have distinct entries, every column should have distinct entries, and all these 3 by 3 I have noted this, I have marked this, these 3 by 3, each row has entries from 1 to 9, each column also has, and each 3 by 3 box. Okay, all of these should have. So here is a Sudoku puzzle, and here is its. Okay, so let's see how you can represent Sudoku in Haskell. We'll just be very naive, we won't try to do too much optimization or whatever. We'll just try to get the correct algorithmic ideas and get a decently working program, which can be improved quite a lot more, but we'll leave it for you to study this problem on yourself. There are lots of resources on the internet for if you search for solving Sudoku using Haskell, and that is a very good way to learn more and more Haskell. But let's look at this solution that we have. This is by Richard Bird. So in one of his Haskell books, Richard Bird is a very prolific author, has written a lot about Haskell, and I think it is in Thinking Functionally in Haskell. Yeah, okay. How do you represent a Sudoku grid? So each digit that you want to store is a character, let's say, and each row is a list of characters, and a matrix is a list of rows. So you have a list where each row itself is a list, right? So that is how you would represent, and you would say that just to be general, we are saying row A, we are making it polymorphic because we will see that we will use this feature. But a grid itself is just a matrix of digit. So every entry here will be a digit, will be a character. But of course, we will only allow characters from 0 to 9, and we also need 1 to 9, and we also need a character for blank, which will use 0 or space or whatever for that. Okay, so at every cell in a Sudoku grid, you will have various choices, right? At any point of time, there are multiple choices possible, and you will have to keep on eliminating one by one, and you can represent the choices, current choices available for a cell. That is a list of digits. Okay, so the aim is to start with a grid of choices, not digits, and then keep pruning the choices more and more so that you end up with a single digit in each cell. And here are the grid entries. So digits is 1, 2, 3, 4 to 9, and I am using hyphen to denote blank. Okay, blank is a Boolean function, which will blank is a function Boolean predicate. It will it's of type digit arrow bool, and what it says is it will be true if the character is hyphen, otherwise it will be false. So far so good. Yeah, So this solution is as presented in chapter 5 of Thinking Functionally with Haskell by Richard Bird. It is an excellent book which you should take a study of after this course, so that you learn more about features of Haskell that we have not covered in this course. And even in the concepts we have covered in the course, you will get much more clarity when you read such a book as Thinking Functionally with Haskell, which is an excellent book. Okay, explains everything very clearly and concisely also. Okay, so the high level strategy is just to generate. Okay, so this is one very high level strategy, which is a very naive strategy, which is to say that I'll start with a grid, I'll generate all possible solutions and pick the first solution. Okay, hopefully there is only one solution, because Sudoku, they guarantee that solutions are unique. How do you generate all solution? Expand the given grid. You have a grid like this. Most entries are blank. Some entries have some 3, 4, etc. Instead of blank, you should put all possible values there, and then that will. So for each choice of values that you put in each cell, that will be one matrix. So then you go and check whether that matrix is a valid solution. What does it mean to be a valid solution? Of course, the rules of Sudoku tell you what a valid solution is. Every row should have unique entries, every column should have unique entries, and every 3x3 box should have unique entries. How do you expand the given grid to all possible valid complete grids? Fill in each empty cell with choices. Expand the matrix of choices to a list of complete grids. So you originally had this with blank entries. Right, what you do is, from here you go to, instead of blank entries, it should be digits 1, 2, 3, 4. So instead of single characters, you put a list. Right, so instead of a list of characters, you have a instead of a matrix of characters, matrix of digits, you have a matrix of choices. Right, and what you do is you expand to get a list of matrices, list of from a matrix of choices, you blow it up. How do you blow it up? By choosing all possible combinations. If I have 1.9 as the choices, I will choose 1 here, 1 there, etc. Or I can choose 1 here, 2 in the next, 3 in the next, etc. So I will make various singleton choices, and each such choice will be a matrix. Each such combination of choices will form a matrix. I will go through each of those matrices and check whether they are a valid solution or not. Choose all valid grids from this list. Okay, solve is the program that you want to do, and this is a very high level strategy. What you want to do is filter by the predicate valid. So you first take the initial grid, fill it with choices, expand the choices to give a choices grid will give matrix of choices, expand will give list of matrices, list of grids. And now you go through each grid and check whether it's valid or not. Okay, and you filter out only the valid ones. This is my strategy. Okay, how do you fill a cell with choices? Okay, if the cell is currently blank, then you put in all possible digits. Otherwise, you make it the singleton digit D. That's it. Okay, so that is my choice, filling a cell with choices. map choice will, so I have this, recall, right, map choice will fill all. If I go to each row and say map choice, it will fill each this thing with choices, right, but I have lots of rows in my grid. So what I should do? I should do map of map choice. Okay, so every row in the matrix gets map choice applied on it, and that map choice will fill every cell in that row with all possible choices, right. So to fill all cells in a grid with choices, you do map of choice, and that is my function called choices. Okay, and fine. So now I have a matrix where I have lists here, and I told you that if I have list 1, 2, 3, 4 till 9, I have 3, I have 1, 2, 3, 4, 9. I have somewhere here 1 dot 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 9. What I'll do, I'll choose 1 here, 1 there, 1 here, 2 there, 1 here, 3 there, etc. 4 here, 5 there, all possible combinations like this, and that will give me the that will, if I do one choice for all these choice lists, that will give me one matrix. But there are multiple ways of choosing, so I'll do all these combinations, that will give me a list of grids, and that is done using Cartesian product. Cartesian product is a usual Cartesian product that you see in sets, etc. A cross B means it is the set of all A, B pairs such that A comes from capital A, B comes from capital B, and that is exactly the Cartesian product that we want to use. Except here it's a Cartesian product on list. Instead of giving sets, I am giving a list. In fact, I will be giving, if I have a list of lists, if I have L1, L2, L3, then I want all possible triples, or in this case I want all possible. So let me show you. If I have x1, x2, y1, y2, y3, as one big list, the Cartesian product should produce for me x1, y1, z1, x1, y1, z2, x1, y2, z1, x1, y2, z2, right. So I have a, originally I have a list consisting of 3 lists. If I try to make the Cartesian product, I want to get a list consisting of 12 lists, okay, because 2 into 3 into 2 is 12. So I have to pair each element of the first list with each element of the second list with each element of the third list, and I have to form all such possible combinations. There are 12 such combinations. That is my CP, and the definition is this: CP of empty list. If I don't have anything at all, then my result is the singleton list consisting of the empty list. The Cartesian product of 0 sets is just the empty set. That is what this says. Cartesian product of x's, I have a first list x's followed by x's, which is the rest of the list, is x followed by y's, where x comes from x's and y's comes from Cartesian product of x's. Okay. So to get back to this example, if I have x1, x2, y1, y2, y3, z1, z2, yeah, so I don't need to write this again. So if I try to do Cartesian product of y1, y2, y3 and z1, z2, I should see what I get. So suppose I just do Cartesian product of, this is Cartesian product of the of this list followed by empty, that is but that is nothing but x followed by y is where x comes from z1, z2 and y comes from the singleton list consisting of the empty set. Therefore, this is nothing but x followed by empty list such that x comes from z1, z2. So, I will get, okay, that is my Cartesian product of z1, z2. Now, if I have to do Cartesian product of y1, y2, y3 with this, I will first put y1 before z1, y1 before z2, y2 before z1, y2 before z2, y3 before z1, y3 before z2. So, Cartesian product of y1, y2, y3 equals all those things, y1 z1, y1 z2, y2 z1, y2 z2, yeah, y3 z1, y3 z2, and so on. Okay, so yeah, so that's basically it. This is Cartesian product. So here is an example. CP of 1, 2, 3, 4 is 1, 3, 1, 4, 2, 3, 2, 4. Expand computes the list of all possible grids. So what it will do is, it will you have a matrix of choices. From there I need to go to a list of grids. What I will do is, I will remember that I have a list of rows. Each is a row, but this is also a list of choices, row of choices. So I need to go and apply CP on each row. I need to apply CP on each row, which means that I need to map CP on the matrix, right? On the matrix of choices, I need to map CP, which will go to each row and apply the CP function. But that will produce a list of rows. I have a list of rows. I have a list of rows now, right? So I need to do CP once again over this matrix now to get lots of possible rows. Okay, so I'll suppose there are 5 rows, 5 possible first rows, 6 possible second rows, 7 possible third rows. Then I'll match all of those together, and I'll get 5 into 6 into 7 number of grids. Okay, so that is what I'll do, and that is given by CP map CP, which will do CP on each row, and then map the apply CP on the whole list of rows as well. Okay, that's the thing. So this is expand. Now once I have expanded, I need to go and now I have a list of grids. Now I need to go and filter out the valid ones in it. Okay, so in a valid complete grid, each row has distinct entries, each column has distinct entries, and each 3 by 3 box has distinct entries. Okay, which means that, okay, so checking for distinct entries in a list is no duplicates. No dupes of empty list is true. No dupes of x colon xs is all not equal to x of xs, and no dupes of xs. You first recursively check that xs doesn't have any duplicates, and check that every element in xs is not equal to x. Okay, that is what all says. Okay, all is a built-in function. All predicate applied on empty list is true. All p of x colon xs is px, and all p of xs. Okay. Okay. So now let's look at how to determine whether a grid is valid. A grid is a list of 9 rows. Each row is a list of 9 digits. Okay. How do I extract all rows in a grid? Remember, the grid itself is given as a list of rows. So to extract all the rows in a grid, you just say ID. Okay, that will extract all the rows in a grid. Okay. Now, so if I apply ID, if I have a grid, I will get a list of rows, which is the same as the original grid itself. How do I get columns? For columns, if I have something like this, 2, 3, 4, 5, 6, 7, 10, 11, 12, then what I need to do is, this should become 2, 5, 10, 3, 6, 11, 4, 7, 12. Right? And how do I do that? So the way to do it is as follows. So go to the last, so this is a recursive function. So if I need to find the columns in 10, 11, 12, that will become, there are 3 columns, right, and each column is a list 10, 11, 12. And now columns of 5, 6, 7 followed by 10, 11, 12, I will attach 5 to the first list in this 10, namely 10, I will attach 6 to 11 and I will attach 7 to 12. So that should give me 5, 10, 6, 11, 7, 12. Okay, and similarly for the others, and the program is just this. If when I have a singleton list, the columns are all the elements made into singleton list themselves. Okay, that is like going from 10, 11, 12 to list consisting of the singleton list 10, the singleton list 11 and the singleton list 12. Calls of excess followed by excesses is, first you determine calls of excesses, that will give you some list of lists, and then you zip with using column excess and that. So 5 will attach to this list 10, the 6 will attach to the list consisting of 11, 7 will attach to the list consisting of 12, okay, and so on and so forth. Okay, so yeah, call of 1, 2, 3, 4, 5, 6 will give you 1, 3, 5 and 2, 4, 6. Okay, that is to extract all the columns. How do I extract all the 3 by 3 boxes? Okay. Okay, so the 3 by 3 boxes are extracted using some complicated looking program like this. Okay, what I need to do is I need to take each list of 9 entries and group into 3 entries of 3 each. Okay, into 3 sublists of 3 each. Okay, so that is what this group is doing. Group of empty list is empty list, group of excess is take 3 of excess followed by group drop 3 of excess. Okay, so you given a list of 9 entries, I will make it into 3 lists of 3 elements each. Okay, now what do I need to do? If I have a list of rows, right, which is my original matrix, I need to go there and make these 3 sublists, which means I need to go on map group. Okay, map means it will go to each row and do this, and then I need to group this itself, this whole thing itself, which means that I have 3 entries here. I will make these 3 as one part and another 3 as one part and another 3 as one part. Okay, so I have split it into some 3 bands of rows. Okay, first 3 rows form a band, second 3 rows form a band, third 3 rows form a band. I have done this, and now I will go and map columns. What it will do is it will I have a picture which will illustrate this very clearly on 2 by 2 matrix, on 4 by 4 matrices. What it will do is it will make now if you think of this as a 3 by 3 matrix, you are just transposing it. So this will go here, that will go here, this will go there, this will go there, etc. Okay, so and it will do this for every one of these bands. Okay, and then you have to ungroup. Ungroup is just concat. I will show you by an example how this actually works. Okay, and the example, it's easier to visualize 2 cross 2 boxes because it's easier to draw the figures. Suppose I have, this is my matrix A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Finally, I want a list of boxes, which means that the first row should become A, B, E, F. The second row should be C, D, G, H. That is this 2 by 2 box. This is the first 2 by 2 box. Then I, J, M, N. And then K, L, O, P. This is what I want. From there, I want to produce this. Now, if you read each row here, it will be a 3 by 3 or 2 by 2 box in my original matrix. Okay. How do I do this? I first do a map group. So, it will go into each row and map it according to groups. Now, earlier in the 9 by 9 case, the groups would group it into lists of size 3 each. Now, it will group it into lists of size 2 each. Okay. So, I will go and do that. It will become AB will become 1, CD will become 1, EF, GH. So, those will be sublists, IJ, KL, MN, OP. Now, there are 4 rows now. You again do a group here. What it will do is it will keep the first 2 rows separate and the third and fourth rows separate. Okay, if I do group on this, I will get this. Now, if I do map calls, it will go there and map calls. So, it will become AB, EF, CD, GH. Okay. Yeah, but there are still gaps. I need to fill in the gaps. To fill in the gaps, what I do is I will fill in this gap first. So, I have to do ungroup. Ungroup is just concat. Okay. So, it will just put this together. Now I do map ungroup, that will go inside each row and put them all together by using concat. Yes, now I have fulfilled my original aim, right. So this ABEF, which is the 2 cross 2 box, is here. This KLOP, which is the 4th 2 cross 2 box, if you will, is here. Okay, so that is how I transform these matrices by using this function boxes. Okay, good. So now I have a way of extracting all rows, I have a way of extracting all columns, I have a way of extracting all boxes. So boxes is just this program that I showed here, and valid of a grid is a predicate. It just checks that all rows in G have no duplicates, all columns in G have no duplicates, all boxes in G have no duplicates. Okay, and finally solve is just saying filter valid dot expand dot choices. You first fill in blank entries with choices, blow them all up into a list of grids, and then filter out all the valid ones from here. That is my solve. Presumably that will return a list of grids. Now I will take the head of that, and that is my solution. Okay, presumably that solve itself will give you a singleton list of grids. That is fine. Yeah, so we can just do this. Okay, this is good. This is a complete solution now. Okay, and the main work here was to check when a grid was valid. Okay, that is the main part of the crux of the solution here. So let's just test it. So I have a puzzle which is like this. I present the puzzle like this. It's a list of rows. So it's a list of rows. Each row is a list of digits. So I do this, and if I try, so here this is just this Sudoku example, and its actual solution is this, right? As you can check later using the slides. So now here you have 184572369, no digit repeats, and so on and so forth. You can actually check. But our program is totally useless to do this, because this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. There are 24 filled in entries, filled cells, which is not bad, but our program won't even start on this, even with half the grid filled. Okay, so even if I have filled in 41 grids, let us say, there are 40 blank cells. For each of those blank cells, you will put in 1 to 9, and then you will expand it. You will actually get 9 to the 40 grids, and you have to check each of these grids for validity. I mean, who knows how big 9 to the 40 is? Okay, so it's a huge number. Actually, it is this number. Okay, you can actually go to, if you ever find yourself saying things like, who knows how big this is, the answer is very simple. Go to GHCA and just enter 9 to the 40, and you will actually get the value. Let's just show that. Yeah, so you get this value. This is really huge, and your program is pretty useless. Okay, and half the grid filled is actually quite a trivial puzzle even for humans, right? So in fact, the solution takes forever even for a grid with only 9 blank cells. Okay, if I give you this, I mean, you just by inspection you figure out what all the things go there. It will take you less than a minute or whatever, even manually just by inspection. But if I run this program on this particularly trivial instance of the Sudoku problem, you see that, I mean, these are not latest figures. This was on some different machine some years ago, but the point still stands. This thing, when I ran it, took 500 seconds, 560 seconds, which is almost like 600 seconds, which is almost like 10 minutes. Okay, you shouldn't be taking 10 minutes on a Sudoku problem where each row has only one cell free. I can understand a human taking more time because the human has to actually write, and that takes time. But a computer should immediately fill it in a matter of a minute, in a matter of microseconds. Okay, so this solution is useless. So let's try to improve the solution. Okay, that is the rest of the lecture. Right, so it is it is really indeed naive, rather thoughtless to try to fill in all possible values, all possible choices and then expand it. Rather, what you want to do is, the moment I have choices, I will prune I'll first fill in all the blank cells with choices and then I'll prune them. How do I prune them? This is what we do mentally when we solve Sudoku. If we say that, oh, this cell is blank, then we will automatically scan the other cells in that row, in that 3 by 3 box, in that column, and whatever number occurs in any of these places cannot be a possible choice for this cell, right? This is the pruning that we do. That kind of pruning is what we want to do now. Okay, so rather than just expand choices blindly, I'll fill in the choices, prune them first and then expand them. Okay, and we would like prune shouldn't break our earlier solution. Earlier our solution was filter valid dot expand. Now I have filter valid dot expand dot prune. The two should be the same, okay, in terms of the result, but it should be different in terms of the time taken to compute the result. Okay. Okay, so how do we prune the choices? Exactly what I told, but formalized in Haskell. So consider a row with 3 entries and 6 blank cells. Let the entries be 1, 5, 9. Then the list of choices for the blank cell is 2, 3, 4, 6, 7, 8. Okay. Okay. So if some column has entries 1, 4, 7, 8, then in that, so yeah, so first of all, originally you would have put 1, 2, 3, 4, 5, 6, 7, 8, 9 for all the blank entries. Now that 1, 5 and 9 are occurring in that row, we will just first prune it by putting 2, 3, 4, 6, 7, 8. And then you will look at the column and see if maybe 1, 4, 7 and 1, 4 and 7 occur in that column. 1 anyway is not part of my choices, so forget it, but 4 and 7 can be eliminated and I will get 2, 3, 6, 8. Okay. And if further some entry, let us say 3 occurs in the same 3 by 3 box, we will eliminate 3 as well. Okay. So this is what we mean by pruning. Fairly intuitive, potentially huge savings. Let us see how much it is. Let's figure out how to prune the choices. Okay. So for this, what we will crucially use these identities. If I do rows and then rows, I will get ID, because rows itself is ID. ID composed with ID is ID. But if I take a matrix and if I take its transpose, meaning that let's consider a simple example: A1, A2, A3, B1, B2, B3. If I take its transpose, which is take all its columns, so the first column is A1, B1, C1, second column is A2, B2, C2, third column is A3, B3, C3. Now this is a list of lists, but I can treat it as a matrix, and if I now take columns again, first column is A1, A2, A3, second column is B1, B2, B3, third column is C1, C2, C3. So in other words, calls takes me from there to here, calls takes me from here back there also. So calls composed with calls is identity. Okay. And similarly, boxes composed with boxes is identity, right? Because to go to that earlier example, A, B, C, D, E, F, G, H, will go to a list of lists where each list is a 2 by 2 box, but that list of lists I will write as a matrix. So the first row I will write the first 2 by 2 box, which is A, B, E, F. Second row I will write the second 2 by 2 box, which is C, D, G, H. Third row I will write the third 2 by 2 box, which is I, J, M, N. And then whatever is left, K, L, O, P, I will write. But now if I go here and I take the first box, it is A, B, C, D. Okay, this is the first box here. And if I write it as a row, I will get A, B, C, D on the top. And E, F, G, H is this row, is this box. So that will go here. And I, J, K, L is that box. M and OP is this box. Yeah. So you can see that if I do boxes and then do boxes again, I will get back the original matrix. So it's identity. Okay. So to prune based on boxes, I will apply boxes first. So to my this thing. So I will have a list of rows. I will apply boxes. Now I will get a new list of rows. But in this new list of rows, each row is a box in my original matrix. Now I will prune the row. I'll prune for that row alone, okay. And if I want to prune based on columns, I'll apply columns and then I'll prune each row, okay. Now each row is a box of the original grid, prune each row. And what I need to do is, I need to go back to the, after I have pruned, I need to go back to the original, this thing. I'll have a reduced set of choices, but I'll go back to the original order. And for that, I need to apply boxes again, okay. And similarly with columns and so on. So now that gives me prune is prune by boxes on top of prune by columns on top of prune by rows. First prune by rows, then prune by columns, then prune by boxes. Prune by some function f is nothing but f map prune row and then f. Okay, so you prune each row. First apply f, it will transform your matrix so that each row is some boxes or columns or whatever. Prune each row, then apply the function f again to take it back to the original order of elements. Prune row is nothing but prune row of a row is map remove fixed. So remember that your row itself is a list of choices, list of choices. Each entry is a list of choices. Okay. So now what I will do is I will first determine what are all the fixed elements. These are the elements that belong to the singleton list. So I will have a 3 here, I will have a 4 here. So 3 and 4 are fixed. Okay. And now what I will do is I will go and remove. So I will map this remove fixed from on all elements of the row. Remove excess from D's means that if length of D's is 1, then D's is already part of a fixed element, then I shouldn't touch it, I should just return D's. Otherwise, I will do D's minus minus x, minus minus is list minus. All elements in D's minus all elements in X's. Okay. Okay. So now actually if I try this solution on the on my puzzle where there is only one free entry in every row and every column, then what I actually get is the solution in 0.01 seconds. Okay, I'll demonstrate all this to you later. Okay, so far for the first two solutions, but even this solution is not great on even puzzles with 39 entries. Okay. So long ago I ran it and I ran it for 6 hours and nothing came. So I aborted the task. Maybe you can take a supercomputer and run it, but it's a pointless thing because you should solve this problem using better algorithms. Okay. And this pruning is not enough is what this tells you. Okay. Because even now what you are doing is you are pruning the set of choices, but still you are expanding it out and verifying each grid whether it is valid or not. Rather what you should do is you should expand, after each expansion you should select, you should prune. Okay, this is the, you shouldn't expand all of it in one go, you should expand cell by cell and then do more and more pruning and you should proceed rather incrementally. That is the actual final solution. Expand one cell at a time. Okay, and you have to interleave expansion and pruning. After expanding one cell, meaning that if I have 2, 3, 4 here and various things here, what I will do is I will now create a matrix where I will create a list of grids where there are other things are this, but this will be 2. The other things are all the same, but this will be 3. The other things are all the same, but this will be 4. But now look at this, I have one more fixed entry, so that will lead to more prunings. Okay, so before I decide to expand another cell here, maybe another cell here is 4, 5, 6, but the fact that this 2 is a fixed, this thing leads to more pruning. Leads to more pruning before you can do an expansion. Okay, so you should interleave pruning and expansion. And how do you expand? This is very reminiscent of the graph explanation things that we saw a few lectures earlier. So you start with one matrix of choices, you expand one cell, that will give you a list of matrix of choices. For each of those you do further pruning and you expand them to, you expand one cell in each of them, and it will be like one matrix of choices here. You can expand, you can pick any one cell and expand it and you will get so many choices. For each of these you can expand in multiple ways. At some point you will stop when will you stop? You will stop when all the grids are fixed, all the cells have only one entry, okay, in the list of choices there. At that point you have reached a complete grid, so you will stop. So any path cannot go more than 81 deep, okay, but in practice you won't even go that much because you are pruning stuff along with expanding. So you will go, if each list is a singleton, then you will stop at that point. If each cell consists of a singleton list, you will stop at that point. So and then you backtrack. So this is the same thing. You try to expand. At sometimes you might realize that there is no way to expand at all because there are contradictions, or you try to expand and everything will lead to an invalid grid. So you backtrack. Okay. So this is the kind of thing that you need to do. Okay. So instead of expanding all cells in the matrix of choices, expand only one cell at a time. A good choice for this is the smallest non-singleton cell. Okay. So you now get a list of matrices. Each of these matrices contains singleton as well as non-singleton cells. Prune each of these matrices and expand one cell in each incomplete matrix that results. Okay, and this is the overall solution. Now expand one is what I am calling this. Expand one will take you from a matrix to a matrix of a matrix of choices to a list of matrix of choices. Expand one rows is, so essentially what you want to do is, if I have somewhere here I will have a this list has only 2 elements, let us say. That's a grid element that has, you are saying, oh, either 4 is possible or 7 is possible. Okay, that's only 2 entries, and everything else is either singleton entries or more than 2, I mean clearly more than 2 entries, or it could be 3 entries here. Okay, so I might be having something where I say 3, 4 or 5, and every other entry says it's a singleton entry, meaning that particular cell is fixed, or it has more than 3 elements, or more than greater than or equal to 3 elements. But this is the first. How do you find out the first? Keep going by each row. Look at the first row of, which has a cell which has only 3 elements, and look at the leftmost such cell. Okay, this is what we want to do. From top to bottom, look at the first row where one of the cells has only the least number of choices, and in that row go from left to right and pick whichever cell it is. Okay, the leftmost cell which has that many number of choices. Okay, and that is all what has been programmed in this. Okay, break and so on are built-in Haskell functions. Break will break your list into 2 halves. It will search for the first element that satisfies the property. Everything before that will be one part and everything after that will be one part. So you break the list of rows into those rows where none of the all the elements are either singleton or have more than the smallest number of entries, and so that is rows 1 is all cells are fixed or have more than k choices. Okay, that is row 1. Row is the first row where some cell has k choices. Rows 2 is the rest of the rows, and inside row also these are all the cells that have either fixed or have more than k choices, and this is the cell which has k choices, and row 2 is the rest of the row. So this is my this thing. Break any smallest will break the rows into those rows where none of the elements are equal to the satisfy the smallest predicate, the smallest predicate, and the break smallest will break the row into all those cells. I mean, it will identify the first point where the number of choices is smallest. Okay, smallest C is just C stands for choices. Smallest C just says length of choices equal to n. N is minimum of counts of rows. Counts is you go through the each row, and each row contains a list of choices. Each row is a list of choice lists, You compute the length of each of those choice lists, remove those that are 1 because those are fixed, and now find the minimum of this. Okay, that is my smallest thing, and based on this I can actually split my, once I have a matrix, I can identify a particular cell which has a number of choices to be filled, 4, 5, 6 or 6, 7, 8 or whatever, but that is the minimum number across all non-fixed rows in the matrix. I will take this and I will expand this. Okay, so I am already expanding this because what am I doing? I am doing rows 1, which is all the previous rows, plus instead of this current row, what I will do is all the cells that come before are the same, and here instead of C, earlier it was C's, now I am replacing it with each C belonging to C's, right? And this is a list. So if I had 3, 4, 5, now I will have 3 matrices I will have, where the rest of the things are the same. Here it will be 3, here it will be 4, right? So this is what I am doing. Okay. Once I do this, I need to know whether at this point this is part of a valid solution or not. Okay, and that I check by saying all OK rows, all OK columns, and all OK boxes. All OK just says there are no duplicates in each fixed, right? Look at all the fixed entries in the row and then check that there are no duplicates, that you have not fixed some value to be 1 and another value to be also 1 in the same row or in the same column or in the same boxes. Okay, that is what you mean by safe. Complete means that every entry is a singleton entry. Okay, so you have determined that all the so there are no more choices to expand. Okay, that is what you mean by complete. Now so recall that choices is this function. If blank D then digits else singleton D, this is what we did, and then we did map of choice. You start with the first grid that is presented to you, you apply the choices function. What it will do is it will go to each blank entry and replace it with a list of digits, and then you start your search procedure. Okay, the search procedure searches for a valid complete grid that extends the current grid. So given any grid, it will find some valid complete grid extending this, and search is really that expand and safe. Okay, search will first what it will do is it will prune your matrix. Okay, after it has pruned, it will check whether it is safe or not. The pruned matrix, if the pruned matrix is not safe, you will not make any recursive call or anything, you will immediately say the number of grids, the number of valid complete grids that extends my matrix of choices is 0. So it's just the empty list. Okay, the empty list of grids. If it is already complete, then I need to return a grid, but remember that I have a list of rows. Each row is a list of choices, each row is a list of cells, each cell now is a singleton list. So what should I do? I should turn that singleton list into a normal element, and I can do that by using head. Okay, because head will, that is 2 followed by empty list. So if I do head, it will just return 2, but it is not, I need to first map this map of head on. So if I map head in each row, it will turn this list of singleton lists into a list of elements, but that is for each row. So I need to map of head, okay, on M prime. That will give me an actual list of grids, okay, that I finally want. Okay, otherwise what will I do? Otherwise I will expand the pruned version. Expand one mean expand one cell, expand the smallest cell, but not for one, because right. So so I will expand M prime by one cell, and then I will, the expanding it will result in multiple matrices of choices. For each of them, I will apply the search function and then I will concatenate all the solutions that result. Okay, this is again a breadth first search kind of description. Actually computed right because of Haskell's laziness. Okay, right. So this works very well on easy inputs with 39 cells filled in. I have this. It actually performs very well even on hard puzzles. Okay, quite well on puzzles of higher difficulty. If I have only 25 cells filled in, I will still do it in 0.02 seconds. I can have hardest puzzles where only 17 entries are filled in and I will still see that you still see that it does it in some 11 seconds or so. Okay. Okay, so this is it. So I'll just go through the summary slide and then I'll actually go through the programs and run some of these programs for you. So what we've seen in this lecture is an incremental design of a very non-trivial program. It's a reasonably simple logic and it's close to how a human would solve it. There is nothing fancy here, nothing fancy like some constraint solving this, that. There is no higher mathematics involved here at all. This tells you the power of laziness, how backtracking is easily programmed as a breadth first search, but in actuality it will do it as depth first search. And yeah, so that's it. Let's actually look at the programs in action and then we will bring the lecture to an end. Okay, so here I have various programs. I have sudoku 1.hs. Here I have actually done all the, it's programming all the things that have been shown on the slides. Okay, sudoku 1.hs is this. Sudoku 2.hs will is the improved thing with the prune thing mixed in. Sudoku 3.hs is actually the search strategy where you expand one cell at a time and you interleave pruning and expanding. I have written some actual, I'll try to see how I can upload these this code also. I have written various comments and I have actually done some local derivations and provided more intuition in these slides, in the program itself. Now I have made sure that I can do this with some actual okay, so I have done some input output part also in this. Let's see how it works. So so first thing I'll exit GHCI and I'll actually do GHC of sudoku 1. Okay, I have various exe files which I can use to run. Okay, so I in fact have a whole directory with the sudoku inputs. Okay, so what I'll actually do is I'll run these things in GHCI itself because it's easier. Okay, so I have various sudoku puzzles here. Let's look at trivial. what happened? Sorry. So this is a trivial puzzle. Okay, as you can see, each row has only one empty cell. So let's try this on GACI. Let's try to copy this line. Control C, and let me go to GHCI. Oh. Okay, I'm here. Let me load Sudoku 3. Okay, so one module is loaded. So I've copied this trivial puzzle. Okay, so I can't copy paste this. So how do I do this? Okay, I might have to actually write it. Okay, let's just make these entries and let's let's see, 524398117. Eight nine one 65432. 418 72596. 548 97321. And actually this is already 8 into 4, 32 entries. So I can actually, if I want to leave everything empty, 0 0 0 0 0 0 0 0. Let's try if this works. Okay, that's my grid. Okay, and then I can do solve grid. Okay, so unfortunately I need to quit, go back to that, now do GSA. Okay, so this is not going anywhere. So unfortunately, okay, but I have the Sudoku program itself. So let's start Sudoku 3 and then we'll see what happens. We'll have to now give input one row at a time. So I'll have to just copy the same input again. Thankfully it is there, minus 52439,817. Okay, 8 minus 9165432 41 hyphen 872596. Five 48 hyphen 97321. And the rest of the entries and the rest of the rows I'll just keep blank. Okay, great. You see that you already have a solution. I'm sorry about this. This input output I haven't figured out in Windows yet, but you can just figure out. Normally on a Mac machine which I use, I would just read from these files and have the program run like this. But you can see the point. Let's try one other example as well. So this example is one other instance of the Sudoku problem. Let's just look at here. There is something called 17 given or whatever, 17 givens or whatever. Ah, 17 dot list. Oh, that is all kinds of 17 problems. 17, that's all kinds of. Yeah, so in fact I will include a whole some 50,000 or so puzzles where only 17 entries are given, not 50,000, 9,000 or so, and you can work your way through all of them. So let me just see this. Yeah, so this seems like a reasonable candidate. I shall yeah, so this is how I would do it on a Mac, where I would do input redirection, or Unix, but I haven't figured it out in Windows yet. So I'll have to painstakingly write all these entries down. Let me just do one final thing, and then that would be the end of the lectures. Okay, so I have started it. Let me make the entries. Blank, 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 6 blank, blank, 8 blank. Okay. Okay, that is the first row. The second row is blank 2 and then all blanks. Blank 2, all blanks. Third row is blank, blank 1 and then all blanks. As you can see, there are very few entries here, and manually solving this would be very hard, but also this is a very good challenge for this program. Blank 7 and then there are 4 blanks and 1 blank 2. Okay. Blank 7, 4 blanks, 1 blank 2. Okay. Now 4 rows are done. Then I have 5 blank, 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 3 and the rest are blanks. So everything is blank except for the 7th entry. Okay. So the next row is blank, blank, 4, 2, blank 1. Okay. Blank, blank, 4, 2, blank 1, blank, blank, blank. The next row is 3 blank, blank, 7, blank, blank, 6. Okay, and we are down 1, 2, 3, 4, 5, 6, 7, 8 rows. The final row is okay. So blank, 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 5, blank. Okay, let's now see. So now Haskell will actually interpret this input appropriately, interpret it as a proper grid, and then it will produce the result after applying the solve procedure that we outlined earlier. Okay, it first formats our input and puts it here, and this is one of the harder puzzles, so it should take some time, but not too much. So let's see what happens. Hopefully it concludes quickly, but yeah, so on that successful note, I think we will end our Haskell programming series for NPTEL. I hope you all learnt some of the nicer aspects of the Haskell language. Just to summarize, it's a very nice language. It's a purely functional language where you transcribe your sort of mathematical descriptions of solutions almost directly to code, and there are many features like lists are of course very essential in Haskell programming, but there are essential features like pattern matching, lazy evaluation. Okay, so these are two important things which does all the basic stuff that you do. We have learned some of the basic modes of expression in Haskell, and some rudiments of input output, defining your own data types, etc. We looked a little at how to measure complexity of programs and so on. We looked at a few key algorithms that would be part of any algorithms course or any programming course. Sorting was something that we looked at in some detail, and then we looked at various data structures. Importantly, we looked at binary trees, binary search trees, AVL trees, and then we looked at leftist heaps and so on. These form some some of them are very sophisticated data structures which are part of many which are very crucial part of many implementation of many algorithms. And finally, we looked at we also looked at dynamic programming in recent lectures, And finally, we ended on a fun note by actually programming a non-trivial task, which is to solve Sudoku. Okay, so there is lots more to learn in Haskell. I had promised that we might look at some bits about monad and so on, but these are for a more advanced course. One needs to gain experience, doing basic Haskell, lots and lots of programming with lists, etc., and gain intuition, and then you can explore the more advanced topics on your own or as part of some other course. Okay, there are many resources available on the internet as well, many other courses as well, but we will end our course on this note. Thank you very much for following patiently all through. Okay, all the best. Thank you.